All right, we have made it to week 9 of the Calculus Summer Prep. And to be completely honest with you, the topics that we're going to cover today, the first one here is not really something that you're going to see in the form that's being presented here in calculus, but the overall concept is something that's important. And if you take physics, then definitely this will be something that you would see. We're going to talk about vector notation and how to add, subtract, and find magnitudes of vectors, as well as one individual piece here called the dot product, which is something you would not actually see until Calc 3, I don't believe, and anywhere else. And then the other thing we're going to talk about, and that will be a completely separate video, will be how to take a fraction and decompose a fraction into separate fractions. So that'll be in video 2. That is actually a topic that you will see, and you will see that if you're going to be taking BC calculus of any sort. Okay, so let's go ahead and get started here with vectors. So the first thing we need to talk about is, what is a vector? A vector is something that has both direction and magnitude. So in other words, if I was going to create just a really quick on the side here, if I was going to create just a quick XY axis, and I wanted to talk about the vector that might look like this. So we'll say that we're going to call this the vector, we'll call it n for now. And you put that little half arrow on top of it to notate a vector. We're going to say that the vector might be the vector 1, 2. Notice how the vector is written, by the way. The vector is written in what looks to be kind of like an ordered pair, but it's got the little angled or greater than, less than looking brackets around it. This is still your x right here. This is still your y right here as far as that's concerned. But the difference between a vector is that does not signify a point. What it actually does is it signifies how far you go in the x direction, how far you go in the y direction, and you have to start someplace and end at a specific spot. So for example, if I wanted to take and create that vector 1, 2, I could start at the origin. Okay, we could start right there, and I could create a vector 1, 2, which means I would go 1 unit in the x direction, 2 units in the y direction, and this is where I would end, would be right up here. But what you do is you actually create from the starting spot at the origin a line that goes up to here and then ends. Okay, and we have seen this kind of information in pre-calculus very briefly. But that is your vector. It starts at one point and ends at the other point. The arrow normally in geometry would indicate a ray, and that just means it keeps on going forever. In this case with vector notation, it actually stops right there because the vector itself has an actual magnitude or a distance to it. So there is a length of that vector. That's what a magnitude is. And the basic idea is to find the magnitude. It's just using Pythagorean theorem. I would go however my distance was in the x direction, so that would be this green dotted line here, and then the distance in the y direction would be the green dotted line vertically, and the green distance in the x direction would be 1, the green distance in the y direction would be 2, and to find the actual magnitude, you're just going to use Pythagorean theorem. So you would have 1 squared plus 2 squared equals, and you can call it whatever you want to. We'll just call it c squared in this case because we're used to using a, b, and c. So then you would have 1 squared plus 2 squared, that's 5, equals c squared, equals c squared. So that means if you take the square root, c then would be the square root of 5. Normally, if we took the square root of both sides of an equation, we would have to do the plus or minus, but because this is a distance, there is no such thing as a negative square root distance of something, so it's just going to be the positive square root of 5. Okay, so a couple other things about that vector is, I could also take the vector, and it does not have to start at the origin. It could start anywhere. The only thing that has to be true is it has to maintain its direction and the same length, or the magnitude has to be that way. So I could technically start right up here if I wanted to, at the point 0, 2. As long as I go 1 unit to the right and 2 units up, that's the same vector. It's still the vector 1, 2. It does not have to start at the origin. I could start that vector someplace over here in the second quadrant. Doesn't make any difference. Put it right here. Got to maintain the same distance and the same, the same direction and the same length. Okay. So when you add and subtract vectors, you always put one vector at the end of the, well, you don't always do it this way, but the easiest way to do it is to put one vector at the end of the other vector. So if I wanted to add two vectors together, I'm not even going to know what this vector is specifically, but if I wanted to add a vector to our vector 1, 2, the one that we started at the origin, and I wanted to add this vector, you would simply figure out what that vector is, call it whatever it is, and then you would add it. The resultant vector of that would be in blue here from the start of the first one to the end of the second one. That would be the resultant vector. When you multiply a vector, and this is the easiest thing to do, the math here is actually the easier piece as opposed to the actually looking at this on on a graph. When you multiply a constant, or what's called a scalar, times a vector. So let's say I wanted to take our n vector down here and I wanted to multiply it by 2. Well, the idea is I'm just simply going to multiply both components by 2, because all I'm really doing is doubling the vector. So if I multiply each component, I would get 2, 4. Very simple to do. And if you think about it, the original vector that I started with in red was 1, 2. If I wanted to double it, it's just going to have another vector 1, 2 attached to it. So if I count it out, 1, 2, and then 1, 2, 3, 4 up, that would be at 4, assuming that I drew this correctly, which I probably didn't. I did not draw it to scale, but the idea is this whole thing right here, that would be twice n. So you would just multiply each component by 2. When you add vectors together, you're simply going to add the components. Add the x component, add the y component. When you subtract vectors, same idea. You subtract the x's, subtract the y's. When we get to number 3 and 4, I'll talk about those again. 4 is not something we will usually see. All right, so let's go ahead and look at a couple other things, because you might be looking at these things up here thinking, okay, it says given the vectors a and b, but it's got these i's and j's. I is vector notation for what's called the unit vector in the x direction. So that just means, draw a really quick little thing right here. The I vector simply means 1 unit to the right on the x-axis, like this. Oops, meant to do that in blue. There we go. 1 unit. That's the I vector. And again, it does not have to start at the origin. I could put it anywhere, but it must go 1 unit directly to the right. The J vector means 1 unit in the y direction. So that is vertical. 1 unit in the y direction. That is, that's J. So when I take 2, and in the case of A up there, if I take -2 and multiply it times I, it just means it's going to go 2 units backwards. And then if I take 5 and multiply it by J, it just means it's going to go 5 units up. Okay, the important thing is that we can actually rewrite this in vector notation. I can take A here, and I can rewrite that vector so it's easier for us to read as just -2, 5. Much easier to deal with here. So just know that if you see the I, if you see the J, the I is just the X component, the J is the Y component. That's what you're looking at. So the B vector, if we rewrite it in vector notation, is going to be the vector 3, 4. Okay, much easier to deal with that way. All right, so let's go ahead and do the math. 1, 2, and 3 are going to be really simple, and then 4, like I said, I'll explain to you guys how to do it, but it's not going to be something that you're probably going to deal with, but it's really simple to do. Okay, so 1 is just wants us to take 1/2 of A. So literally, I need to take 1/2 and multiply it by my A vector, which is -2, 5. And then you'd simply distribute the 1/2 into each piece. So 1/2 times -2 is -1. 5 times 1/2 is just 5/2. And there you go. Number 2 says we want to take B minus A. So B is the vector 3, 4. And we want to subtract the vector -2, 5. And that looks kind of like an equal sign. Let me erase that real quick. Redraw that. That's a minus. Okay. So again, subtract the x components. Now don't forget, this is 3 minus a negative 2. So 3 minus negative 2 is like 3 plus 2, so that's 5. And then 4 minus 5 is just going to be negative 1. And that would be the resultant vector from subtracting those. That is a, let me redraw that. That is a 5 in there. My 5s keep getting connected. Okay, one thing I don't like about this pen is it tends to drag the tail a little bit. Okay, and letter 3 and number 3, we're trying to find what looks like an absolute value symbol. When it comes to vectors, that is what symbol for the magnitude. So when you see the bars around something, that means magnitude. And if you think about it, absolute value is also a distance. Magnitude is a distance. They actually mean the same thing, just in different notation. So in this case, we are trying to find the magnitude of vector b. Well, let's go ahead and rewrite again what b was. So b was the vector 3, 4. And we are trying to find the magnitude of that. And the magnitude is just using the Pythagorean theorem. So really the magnitude says we're going to take, in this case, the x and the y components, the 3 and the 4, and square them. So we're going to get 3 squared. We're going to add it to 4 squared. And then if we set that equal to a c squared, you'd have to take the square root. So the magnitude is really just the square root of all that. So we're going to get the square root of 9 plus 16, which is the square root of 25, and there's no equal to symbol here, so there's nothing for us to take a positive or negative of anyway, so we just get the magnitude is 5. And again, magnitude is distance, so the distance of that specific vector, or the length of the vector, is 5. All right, the last one, this little dot right here, normally you would see that and you would think, okay, this is a multiplication, and it is. It's just a different type of multiplication. When we get to vectors, there's different notations and different way to multiply things. This thing right here is what is called the dot product. Dot product. And when you get to higher levels, you're also going to learn this thing which is called the cross product, which, as you would expect, just kind of looks like an X, like a time symbol, but it's different when it comes to vectors. The dot product says what you're going to do is you're going to take the two components of the x's and y's and multiply them individually, but then add them together. So let me show you real quick what I mean. So this is going to be negative 2, 5, that's A, dotted with 3, 4. So what that really means is I take the two x components and multiply them, so that's negative 2 times 3, and then I add that to the multiplication of the two y components. 5 plus 4, 5 plus 4, it should be 5 times 4. 5 times 4. And what you'll notice is we just took two vectors and did some kind of a multiplication. Did some kind of a multiplication, and we're going to get a number out of this. So we're going to get negative 6 out of the first one, and we're going to get 20 out of the second one. When we add those together, we get 14. That's a really, really quick overview of how to do the dot product. You'll get much, much more in depth in this when you get to much higher level math. But there you have it. That's a basic review of some vectors. This comes into play, like I said, in a slightly different way. We do deal with some vectors in calculus. Again, mostly BC stuff, but it does come into play, just not exactly the way you're seeing it here. But this is good enough.